regression trees are like following the exact same principles as the classification trees. The only thing now is though that we need to change the impurity measure that's like based off of like entropy or Gini index or whatever to a more appropriate one, which basically is a distance-based measure. And again, we just have like XM are the items that fall into a certain node, and we need to identify like an indicator variable that basically is 1 if X is there or 0 if it's not there. Okay, but what we basically now have is we need to define a goodness parameter of that split for regression trees, and it's measured as the mean square error of the estimated value GM, which is basically the mean value of all the items in that node. Okay, so we want to know like how close or how variant these values are within one of those nodes. So we calculate the regression value with these index variables. If it's there or not, this counts and divided by the number of items. So that's basically the mean value for all the values in that node, and we then calculate the variance, so to say, of these these values towards the mean value. So like if they're far apart, this value is high, so that's a bad split, and if they're close to each other, that value is low, that's a good split. Okay, and yeah, so then EM corresponds to the variance in a given node, and if it reaches below a threshold, then we can stop. And basically, again, like this threshold that we define here gauges like how complex the tree will become. If you want it to be 0, well then at the end you will have a node for every data point, and if you have it too large, it will be too small of a tree that will have a large error on your training set. And we again define a split. Basically, we split based off of a new node, so that each branch now gets these new indicator variables. We calculate the new mean values, and then we again sum up over all of them and weigh it by the total number of items that we have in there. And we want to find the one split that maximizes the difference here, and that we have like a smaller error in the next one. That should be fairly like similar and straightforward. So we can reuse the previously identified algorithm. We just replace the entropy calculations with this new error metric, which is based on the variance of the items in the tree. And again, like the complexity of the tree is different for varying levels of thresholds, and you can see this here. So if we allow a threshold within each node, and now this is one node, this is another node, and this will be another node. If you allow this variance between all the points that fall into this node to be like larger or like less or equal to 0.5, then you would find like a tree that has like these 3 nodes. If you want to reduce it, well, these are not too far apart, so they would fall in and together, but then these two are kind of like outliers in this set, so they would define a new split. They would get into a new location, and if you go further and further down the line, you would require more and more new data, new splits. And in this case, you have 1, 2, 3, 4, 5, 6, 7 nodes in the end. This looks like this basically. In a regression tree, you're deciding greater or equal most of the time, or greater or smaller, and again you're jumping over like yes or no, and then instead of a class you just have a value in here. Okay, and that's basically how you define these regression trees. obviously the regression tree will always only output a value that is actually written in there, and this value is defined as that GM value, so that would be the average of the data points in that region, okay? You can also have more complex trees, obviously, and that can go even further. And we can define methods and strategies to remove, for example, this part of the tree that might be a bit too complex, and we might not need it. And the way to do this is basically, it's again quite calculation intensive. But for example, what we would do, we would hold out a subset of our data as our validation or pruning set, so to say, and then we would run the pruning set through this complex tree and would identify, for example, that this node has exactly the same performance as if we remove these two nodes. Okay, so if we just define here that this node now puts out a number instead of creates another split, then we would basically remove these two here and define that this now produces the average value of the items in this like parent node. Okay. And that can only be done if you actually have a left out pruning set or a validation set. And for like that, it is important that you keep a set for that. And again, you could revalidate that. But also you can define, for example, you can say I want to stop always at this level because it has the depth of like 1, 2, and 3. I don't want to go further than depth level 3 for the decision trees, for example. You can also say I want at least 10, 20, 5 samples in each leaf node. So if a leaf node, for example, ends up to have just 4 items, it would stop. Like it would not go further, and so on. So you can define these different types of thresholds to gauge like what is the right size of the tree. And again, you have to validate the depth and the number of items in the leaf nodes at minimum, or at each node at minimum in your like validation and machine learning procedures, in the experimental procedures. Okay. I promised also that we're going to talk a little bit about like how you can use trees to extract rules. So for example, here, what is the, well, these are just some values, I guess, and what we could do, for example, is, how do you get to this one? Well, 0.8 is the value if the age is greater 38.5 years of age, and the value is years in job is greater to 0.5 years than 0.8. So you basically create a rule for this 0.8, and you say if age greater and years in job greater than 2.5, then 0.8, and basically this is how you derive 5 rules. For each leaf node you would derive 1 rule, and I think this is like the risk of, or the certainty that the person is not going to default. Yeah, it's just basically you can go through all these decisions at each node and just sum them up through ANDs, logical ANDs, and you can come up with more or less complex rules here. And basically a tree is nothing but a collection of these kind of decision rules. Does that make sense? Okay. Yeah, in a classification tree, if you, for example, had like class 1, class 2, class 1, class 2, class 1, you can then take the rule for coming here, or the rule for coming here, or the rule for coming there. Okay, so that's kind of like just a little additional thing here. So yeah, for example, you would combine this for the tree that we had in the example. Okay, so you combine, if you have class 1 here and class 1 here, you would combine the two logical paths just through a logical OR to come here. Okay, and then again, if you have multivariate trees, you could use different kinds of functions. So for example, you can make linear decision functions, you can make quadratic decision functions, etc. Yeah, you can even have like neural networks or spheres, and you can have like a whole hypothesis space in each of those decision nodes, and basically can come up with more and more complex solutions. And for the example that we had in the beginning, you basically just come up with this linear function here, which has a weight for x1, for x2, and a bias to move it away from here. Right? So you can come up with more and more complex decision nodes here. And yeah, that's it for today. Yeah, good luck at the career fair.